Welcome to the second user training video for Conjecture System Identification, a program that helps you take the data from your industrial systems and create simple models of best fit. In our previous training video, we went through the main features of Conjecture System Identification and how to use the program to build and select models for a dynamic industrial system with a single input and single output. We will be building on that understanding in this video. The system in the previous video was a linear system, where the output changes in proportion to the input change. In this example of a linear system on screen, the output change is always double the size of the input change. The doubling effect holds no matter whether the input change is big or small. The water pump system you saw in the previous video was largely linear in nature. However, while some industrial systems are linear in nature, many are not. In these cases, the size of the output change is disproportional to the size of the input change. A small input change may cause an output change that is, say, double in size, while a larger input change may cause an output change that is, say, only 1.5 times its size. We can use conjecture to model these systems as well, but we will need different methods. So in this video, we're going to focus on modeling for nonlinear systems, and following on from the previous video, we'll look at this for systems with a single input and single output. To illustrate a nonlinear system, we've built an air pump system from which we draw our data. We have a 2-meter tall clear acrylic tube in which we want to suspend a ping pong ball steadily at a given height. We do this by pumping air up the tube at high velocity using a motorized pump and varying the duty cycle of the pump motor, which is the percentage of time in which the motor is on as opposed to off. Our input to the system, therefore, is the pump motor duty cycle, going from 0 to 100%, and our output is the ball height within the tube in centimeters, measured by an ultrasonic sensor in the bottom of the tube. We use a PID control algorithm to vary the pump motor duty cycle using feedback from the ultrasonic sensor. You can find the data for this system in the Conjecture folder. Click on Training Data, then the Air Pump folder. The data is stored in the CSV file called airpump_1. First, we're going to click on the airpump_1 text file to look at the information available on this dataset. So here we have the dataset name and a general description, and then the sampling interval. Now in this case, that's every 200 milliseconds. And then we have the data elements. So in column A, we have the output from the process, which is the height of the ball in the tube in centimeters. And then in column B, we have the input, which is the pump motor duty cycle. Again, you can see that this follows the format of the data file that's required for loading into Conjecture. So now we go back to our air pump folder, and we'll click on the airpump_1 CSV file to open it in your spreadsheet application. You'll find that the first column has the output data, and the second column has the input data. So if we were to plot this data from the air pump process, here we're going to look at both the input and output on the same graph. You'll be able to see this in Conjecture as well once you've run a model calculation, but I like being able to just visualize the data first to get an idea of what models I might try to fit. So here we can see very clearly how the timing of the spikes in the input relate to the timing of the spikes in the output, maybe with a slight delay. No matter whether your system is linear or nonlinear, it's always good to start by fitting a linear model, like we did in our first video, just to get a base reference from which you would try any other models. So let's open up Conjecture from our desktop and get the main window. So we'll start with the model setup in a similar way to how we did with the water pump system. Click Load CSV File, and locate your air pump 1 data file. Then select it and click Open. This loads your data into Conjecture. Click Restore to see the default settings and see what comes up in the fields below. So we get the same defaults that we had for the single input system in our previous video, as well as the same hypothesis equations. We're going to build a model with our defaults, similar to what we did for the water pump system. We'll use the default input shift, which is the minimum shift possible. This corresponds to 200 milliseconds, which is the time interval. We'll also keep the default filter shift and make sure the output shift box is checked, as we want to include an output shift in our model. And the last thing we'll do before running the calculations is to have a quick look at the initial conditions. So we have the first guesses for big A, big B, from your first hypothesis equation, and then the initial condition for small a, which is the output shift that comes last. So now we're ready to calculate. Ensure that the plot model radio button is on. It's usually on by default. And then we hit calculate. All right, so now we have our plot and some results. Let's open up the plot to view it in full screen. So we have the process output in blue, and the model output in green, and our input in red. So here we can see that the model is really not a good fit to the data. It gets bits and pieces of the shape right, but overall the peaks and troughs of the model don't reflect those of the process. It's significantly higher in some places and lower in some places. And also if you look in the places where they do match up well, like here for example, there's a slight horizontal shift, which indicates our input shift estimate isn't quite right. So you can save this if you like. For now, we're going to close this and go on to the results. And we can see that Conjecture has estimated values for A and B, and for the output shift as well. We also have an estimate of the gain value, which is interpreted in a similar way to the single input system in the previous video. However, since the gain is derived from the model estimates, it is only reliable when the model is of a reasonably good fit. And since this model is such a poor fit to the process, we won't look further at the gain at this point in time. So one reason for this poor fit is the non-linearity of the air pump system. The higher the ball already is in the tube, the more air we would have to pump in to raise the ball further. So an increase in output from a higher starting level would require a greater input change than a similar increase in output starting from a lower level. With systems like this, we need to apply a transformation to the input data before loading the data set into Conjecture for modeling. There are a couple of possible transformations we could use. One is a power transformation, so for example, taking the input to the power of 2. A root transformation, for example, taking the input to a power of 0.5, also known as a square root. And then there's the logarithmic or log transform, and we normally use the natural log for this. Now it's completely up to you which transform you try first, and it just depends on what you know about the properties of your system. But for this system, we're going to try a square root transform first. So let's go back to our air pump CSV file. We want to calculate the square root of the input, which is in column B, and put that into column C. So let's do that. So we want the square root of column B. So just B1 to the power of 0.5. Enter, and then we double click on this handle to populate the whole column. And then let's copy this and paste just the values into column D. And we'll select paste values only. And then we'll go ahead and delete columns B and C. So now what we've done is we've replaced the original input data with the square root transformed input data. We'll save this as a new CSV file let's say air pump square root, CSV, for example, and then we'll close. So now let's try a model in Conjecture. So go back to our Conjecture main window and load in this new CSV file. So we'll click Load CSV, and we'll select this air pump square root CSV, and click Restore to get the defaults, and we'll just use these defaults now to build a new model. So now we have a plot and some new results. Now this plot still isn't a great fit, but it's better than the first one, as you can see. At least now we're getting the general shape of the model mostly right. But if you take a closer look at these highlighted areas, you notice how the input peaks several times in a row, which then causes the output to peak several times in a row, but as it peaks, it gets higher and higher each time. So this means that successive input changes actually have a cumulative effect on the output. And this property of our air pump system is something that we need to consider in order to refine our model further. So in our system, say we crank the input up to 100% for a short period of time, and we do this several times. Each time we do this, our output gets higher and higher, even though our input change each time has been the same. So what if, instead of charting the output values themselves, we only charted the change in the output? So you can see here, each time we increase the input, it results in a change in the output, a rise in the output from its previous level. As the output level reaches steady state, this change in the output goes back down to 0. And then the same pattern occurs when we crank up the pump model again for a particular period of time. And what we've done here is to create an output variable that is actually more proportional to the input changes. Because as you can see, these input changes result in output changes that are of a similar proportion each time we have the input change. This mimics the data that we would get in a linear system, which allows us to then get a better fitting model in Conjecture. So let's go back to our air pump square root data. And what we're going to do now is we're going to make the output of our process the increase or the change in the output rather than the output itself. So we're going to use the increase in ball height between the current and the previous time point. So let's start in cell C2. And what we're going to do then is we're going to start with the current time point being time 2. And then we're going to subtract the output at time 1. And click enter. And then double click the fill handle to fill the entire column. What we can do now is we can copy and paste these new outputs into column D, just the values only. Delete column C, and then cut column C, the new column C, and paste the values into column A. So what we've done now is we've replaced the values of the output data with new values of the change in output. So the very first output value will be blank. Let's just put a 0 in there. And let's save this as a completely new file. So let's make it air pump underscore square root underscore y deriv, say. Since we've taken the derivative or the difference of the y's, i.e. the outputs. Now if we were to plot this new data, this square root y deriv data and compare this to the original data, it now looks very, very different. So firstly, we've applied a square root to the inputs to deal with the first nonlinearity problem. So the input values are now on a much smaller scale than they were in the original data set. And secondly, we've also made the outputs a derivative. So the change in ball height instead of just the ball height itself. And what these transformations have done is to make the input changes and the output changes more proportional to one another. And that's what we want in order to fit a model in Conjecture. Okay, so now to go about fitting this model, back to our main window in Conjecture, and let's load in the square root y deriv CSV file and click Restore. And then we'll calculate the default model for this. Now, this is a far cry from the model fit that we first had. You can see here now that this model fits the overall pattern of the process much better than the previous models we had. To some extent, it actually smooths the process out. So it's cutting through some of that noise in the data, but it also picks up most of the main trends, which is the important thing. I'll leave you to zoom in and examine the plot in more detail and to save it if you want. You may notice when you zoom in on some of the peaks and troughs in the plot, the model actually sits slightly to the left of the process. You might be able to see that here. So it sits slightly to the left in some of the peaks and troughs. This can be an indication of more delay in the process than we estimated. So you may want to go back to the model setup after this and increase the input shift to see if that fits better. But for now, let's just look at the results. As always, the estimates for A, B, and small a will let you form a model equation for your system. Now, once you apply a transformation, or in our case, two transformations to your data, the gain can become pretty difficult to interpret with regard to duty cycle and ball height. However, because our model fits relatively well, it becomes a very useful model for improving control. To see how we do this, or one way we can do this, check out our video demonstration of the air pump system. A link is provided in the video description. Now at this point, you could play around with the input shift to see if you can improve on our estimation of the delay in the system. Another thing you could do is try other root transformations of the input to see how they fit. In your air pump training data folder, we've actually included some data sets that use a 0.7 root transformation, which is the one that we use in our video demos. Remember that you can find a list of results for all the models that we fitted in this session by going to the Conjecture main window, clicking on File, and then Results List. We've covered a lot of material in this video, and hopefully this has given you some ideas on how to model systems with nonlinear properties in Conjecture. We looked at two characteristics of our air pump system that we needed to consider. Firstly, when the input changes and output changes are not proportional. And second, when successive input changes lead to cumulative output changes, which means that the output gets higher and higher. To make the data easier to model, we can try a transformation to the input data. There are several we could use, or we can take the derivative of the outputs, for example, the ball height, and then subtract its previous value and make that the output instead. It can take some trial and error to figure out how to best model a nonlinear system, but we hope that the methods in this video and the simplicity of model building in Conjecture itself will help to make this a smoother process. We'll go through more tips on how to fit and refine your model in our video on checks and troubleshooting. In the meantime, our next video tutorial will look at modeling for systems with more than one input. If you have questions or feedback on this video, please contact us at Conjecture Data Solutions. Thank you for watching, and we hope you enjoy using Conjecture System Identification.